Hello and welcome back to the Science of Concrete Materials class. This is lecture number 20 of the class, and we will continue our discussion on the chemical admixtures. So one of the major, as we mentioned before, one of the major disadvantages of concrete is its susceptibility to damage during freezing and thawing cycles, when it is in a saturated or near saturated condition. So concrete can be badly damaged after a single winter's exposure if corrective measures are not taken. And this rapid deterioration would effectively preclude the use of concrete in most major applications, such as pavements, dams, foundation, and so on. And all porous materials such as brick, ceramic tiles, and the like suffer from the same deficiency unless the material is especially designed to resist freezing and thawing, or otherwise the frost resistance. Fortunately for us, concrete can be made frost resistant by the addition of air-entraining admixtures, as we will see in the next slide. Okay, so all concrete designed for outside exposure should be air-entrained routinely in the northern United States and throughout Canada. So the mechanism of frost protection is described in detail in later parts of the class, although I will touch upon it briefly when we talk about, we will discuss it more in details when we talk about the durability. Here in this lecture, we are only concerned with describing the effect of air-entraining agents on concrete properties. So if you look at this slide right here, it shows the difference in durability of the concrete between the non-air-entrained concrete and the air-entrained concrete. As we see here, the air content increases the relative durability, which comparing one concrete to another, how it is increased with the use of air-entrainment. Okay? So air-entraining admixtures increase basically the amount of air that is incorporated into the concrete during mixing. So the volume of air required to give optimum frost resistance has been found to be about 9% by volume of the mortar fraction, as I will show in the next slide. There is a table, I will show it. So although the air is usually entrained within the paste fraction, but when we calculate the air volume, it is based on the mortar or the concrete, as you will see. Typically, and for routine field tests, the easiest quantity to measure is the amount of air expressed as percentage of the concrete volume, as I said. So the air content must be in the range of 2 to 8% by volume of concrete for satisfactory frost protection. The actual amount depending basically on the maximum size of aggregate being used, the coarse aggregate that is. So this is because more paste is required in this case to provide workable concrete with a lower maximum size of coarse aggregate. Okay, so that's the size of the coarse aggregate impact the air content because of the workability issue. The air content measurement, includes voids naturally entrapped within the paste during mixing. So the entrapped air is different from the entrained air. The intentionally entrained air increases the total volume of air voids by about 3 to 4% of the volume of the concrete, and it is distributed in the paste as very fine bubbles. So if we look at this table, as I mentioned, this is the characteristics of air-entrained concrete, optimum frost resistance. This is for a mix, with a cement content of 307 kilogram per cubic meter. It shows here the optimum air content and how it's measured in relation to as a percentage of the volume of the concrete, the mortar, and the paste. And I said it's reported typically or counted as percentage of the volume of the concrete. As you can see, when we decrease the maximum size aggregate, you could see an increase in the optimum air-entrained content, or the required air-entrained content for optimum for frost protection. See this increase right here. So this is here the air volume contents, as per SEI. This is the air content for non-air entrained concrete. You see we said it increases it by 3 to 4%, as I mentioned. And here it's the measured air content, percent by volume. This is of the concrete volume, here of the mortar volume, and here is the paste volume. And here it shows the bubble spacing factor. You see how it increases. This I will define in a couple of minutes. So let's look at the air, the entrained air void system. The structure of the air void system is critical basically for the satisfactory performance of concrete under freezing and thawing conditions. So air-entrained concrete cannot be distinguished basically from non-air entrained concrete with the naked eye. If you look at cross-section, you cannot tell the difference. Because of the fineness of the bubble system. So when viewed under a microscope, as this figure right here, tiny bubbles can be seen randomly dispersed throughout the paste. They are approximately spherical in shape and range in diameter from 0.05 millimeters to 1.25 millimeters. So it looks as if the paste has been blended with a fine foam, and this essentially what happens. It's just like a foaming agent we add in order to create these bubbles. The air-entraining agent, causes the water to foam, stabilizing the bubbles so that they are locked into the paste during hardening. Okay, so a good air void system will provide literally millions of bubbles in a cubic meter of concrete. Okay, as you can see, this is a view under a microscope, and it shows here the air bubbles throughout the paste, a fraction of the concrete. Okay. So let's look at the critical parameters of the air void system. The critical parameters defining a satisfactory air void system are the spacing factor, the specific surface area, and frequency, which are determined, basically microscopically in accordance with ASTM C457. Okay, these are the three critical parameters: spacing factor, specific surface area, and bubble frequency. So let's look at the spacing factor, denoted as L with bar on top of it, defined as the average distance from any point in the paste to the edge of the nearest void, and it should not exceed 0.2 millimeter or 0.008 of an inch to ensure adequate freeze-thaw protection. I will show that on the next figure, on the next slide. The specific surface area, denoted as alpha, and the bubble frequency, denoted as N, are interrelated and reflect the mean size of the bubbles, basically. So in a protective air void system that will perform satisfactorily, alpha should not be less than 25 millimeters square per cubic millimeter, and N should be about 0.3 to 0.6 per millimeter. Okay, so although the spacing factor is the most commonly used parameter, all three target values should be achieved for a properly entrained concrete. All three values, so that this will ensure basically a well-distributed system of small bubbles that protects the whole paste volume. These values mentioned here are attained when the recommended air contents okay, let me go back here, I'm sorry. These recommended air contents here, as I mentioned, in this table, are maintained basically using an air-entraining agent from a reputable supplier, a well-known material to perform very well. So these, those values can be attained when we provide the values recommended in this table. Okay, and here is what I talked about, the spacing factor, and this is the concept of a spacing factor. We said, from the average distance from the point, any point in the paste to the edge of the nearest void, something like this. Okay, and this, its effect on the effect of the spacing factor on durability. Durability factor, a value, arbitrary value, and see how it's impacted. As we increase the spacing factor, the durability factor decreases, and as we said, for satisfactory performance should not exceed 0.2 millimeter, something around that range right here. But as you increase the spacing factor, durability factor decreases. Okay, keep that in mind. So also as we mentioned about the microscopic examination, the quantitative microscopic examination, as per ASTM C457, can be carried out routinely to determine these parameters, as we mentioned, using automated computer-based system. Although in the field only the total air content is controlled, so you have to keep that in mind. Some concretes, for example, containing superplasticizers, may show good frost resistance, even when the air void parameter limits are exceeded. Okay, also. So alternative parameters that, give estimate of the fraction of paste protected have been proposed to account, for the random distribution of air bubbles in the paste. But I'm not sure if any have been adopted by ASTM standards yet. Okay? I'm going too fast. Let me go back. So, okay. Let's talk about really the air-entraining materials. As can be followed from the preceding discussion, that air-entraining admixtures must contain compounds that will promote the formation of stable foams within the paste. Bubble formation in water is normally a transient phenomenon because the high surface tension of water, opposes the creation of air-water interface that bounds a bubble. So they're not stable with water just alone. Foams can only be formed in the energy barrier represented by surface tension can be overcome, so the masses of stable bubbles can be created during agitation. Okay, so again, foams can only be formed if the energy barrier represented by the surface tension, which I talked about, can be overcome, so the masses of the stable bubbles can be created during agitation. So air-entraining agents contain surface active agents that concentrate at the air-water interface. It lowers the surface tension so that bubbles can form more readily and stabilize the bubbles once they are formed. All right? So let's look at these surface active agents. The surface active agents, also called surfactants. I know it's a strange phrase, but it's cool. Surfactants basically are molecules with one end. At one end, they have chemical groups that tend to dissolve in water. They call hydrophilic or water-loving. Okay, something, it's represented by this schematic, something like here. So, okay, we said these hydrophilic or water-loving, that dissolves in water. Okay, while basically the rest of the molecule is repelled by water. It's called hydrophobic or water-hating. Okay, this is the other end of it, which is the hydrophobic component. So the molecules tend to align at the surface. It tends to align at the air-water interface with their hydrophobic groups in the water, and the hydrophilic groups in the water, and the hydrophobic portion in the air, as you can see here. Okay, these are the hydrophilic, they are dispersed in water, and these are the hydrophobic on the other side, in the air, within the air bubble. So these basically are, like carboxylic acid or sulfonic acid groups, are commonly responsible for the hydrophilicity of the molecules and are attached to hydrophobic, aliphatic, or aromatic hydrocarbons. That's how we create this strange mix of a surfactant, as you can see here, described in this comment. So air-entraining admixtures basically are closely related to synthetic detergents, although the foaming capacity of the detergent is only a side effect of other surface active properties. Most household detergents cannot be used as air-entraining admixtures. Remember that. Do not use household detergents. Because the foams are too coarse, large bubble size, and not sufficiently stable to remain intact while the concrete is hardening, in addition to many other factors, of course. So, since many commercial air-entraining admixtures, basically are prepared from byproducts of other industries, for example, pulp and paper, petroleum, and animal processing, the active ingredients may only be a fraction of the total admixture. You remember I talked about the dosing and overdosing. So because the admixture acts only at the surfaces, a little goes a long way. That's why the active ingredient is, very, very small of the total component of the admixture. Since typical dose is only in the range of 0.005 to 0.05% of active ingredient by mass of cement, admixtures are often, pre-diluted to assist accurate batching and are added to the concrete with the mixing water. So that's one way to control the dosage and prevent overdosing is to pre-dilute it in set amounts and to add it to the water in order to mix it well. Some manufacturers also intergrind air-entraining agent with the cement, as I mentioned, to obtain air-entrained to obtain air-entrainment directly on mixing with water without the need for an admixture. Such cements, designated as the 1A, 3A, or remember we talked about those during the cement types. But they may not always entrain sufficient air and should not be used without being tested under job conditions. Remember, the use of any admixture or additive should be verified with a trial batch using the same material, the same job conditions. The use of the air-entrained cements may not actually give the desired results. So because of this, limitation, the use of air-entrained cement is only limited to small jobs, not to large-scale jobs. So it's better to add it as an admixture to the mix. So how, I'm talking about this, I will talk about this during the durability, but I'm mentioning it here just for early reference as far as how these air bubbles protect the paste and the concrete from the effect of freezing and thawing, and how they provide basically sites for the expansion of the ice during freezing, and in order to prevent these expanding ice from cracking the concrete. Okay, we will talk about this in more detail later. So let's talk about the factors that affect air entrainment. We said, any admixture you use will be impacted by many other properties and parameters of the concrete. So air entraining admixture should always, as I said, be tested under field conditions, because the amount of the entrained air it provides can be affected by a variety of factors, as you can see here. Slump, the temperature, the aggregates, the fine aggregate content, mixing time, the vibration, all these affect the dosage, the amount of material to be used. So the admixture dose can be adjusted to bring the air content within the recommended limits based on what goes on during the handling and the mixing of the concrete. So increasing the admixture dose will invariably increase air content, will decrease bubble size, and will decrease the spacing factor. But again, you have to consider the other factors, how it affects it. Okay, so the variety of surface active agents present in the commercial admixtures means that job conditions may have different effects on the different admixtures. Again, we said testing is key. As you can see here, almost every property or parameter of the concrete affect the air entrainment admixture dosage. So let's look at these one by one and see the impact of each component. So let's look at the effects of the materials. The air entraining potential of an admixture depends on the concrete materials used and their proportions. Finely ground cements entrain less air than do those ground more coarsely. So the fineness of the cement impacts it. Similarly, a high proportion of fines in the fine aggregates, or the addition of finely ground, finely divided materials such as the mineral admixtures, fly ash for example, will also reduce the air contents. Usually more air is entrained in concretes with a high sand content. Okay, as you can see here in this figure right here. Right here, it's clearer. So we said more air is entrained in the concrete with high sand content, but the gradation, between, for example, material between 600 micrometers, the number 37, and the 300 micrometers, number 57, is the most effective. So again, that's something you need to know. Trial mixes will help. And the particle shape of the aggregate will also affect the air content. Impurities in the mixing water or in the aggregates may have positive or negative effects on air entrainment. So again, that's something should be considered. The use of other admixtures, though, simultaneously with air entraining agents should be approached with caution, because they may affect air entraining abilities of the admixture. So when water reducing agents are used, the dosage of air-entraining agent frequently can be reduced while maintaining a given air content. Okay. Also, some common chemical admixtures, for example, superplasticizers, may interact when mixed with air-entraining admixtures and inhibit entrainment. In such cases, the second admixture used in addition to the air-entraining admixture should be added to the concrete after the air has been entrained. That's one way to deal with it. Also, the carbon, remember we talked about the carbon content in the some of the SCMs. The carbon present in fly ashes will suppress air entrainment in air-entrained concrete. Cement content has also a marked effect on the total air entrained. Okay, so at a given dose, lean concretes entrain more air than do rich mixes, and low water cement ratio concretes entrain less air than concretes with high water cement ratios. Okay, so those things really, as far as the materials effect goes, those what I just mentioned here should be looked at: cement content, cement fineness, water cement ratio, the fine aggregate content of the total aggregate, the fineness of the fine aggregate, the use of mineral admixtures such as fly ash, which affect both generally because of its fineness and because of the carbon content, and also the use of other admixtures. And again, the key to verify all this with proper testing, doing trial batches, to ensure any possibility is being known and mitigated before you go on with bulk production. This is what I talked about here, about the aggregate, the fine aggregate content. As we can see, as it increases the air content of the concrete mix. So, okay, so we talked about the effect of the material. Let's talk about the mixing and consolidation. Let's look at the mixing time. Air entrainment occurs while the concrete is being agitated during mixing. Okay, so the total volume of entrained air depends on the type of mixer, and the rate of mixing and the amount of concrete being mixed. All those make a difference. Again, testing and trial batching. So the time of mixing is also important. So the air content will initially, as you can see in this figure here, time of mixing and air content. The air content will initially increase with time and then gradually decrease. Maximum air entrainment is generally achieved during normal mixing times. And if the air loss should occur during extended agitation, during the transit of ready mixed concrete, this can readily be allowed for by adjusting the admixture dose. I mean, there is the transit mixers, from the time they leave the mixing plant until they arrive at the job site. This time may be increased. So basically, and I go back to my key point, trial batches, trial mixing. In case you have extended mixing time, you may have, as I said here, adjust the dosage in order not to miss the optimum dosage required to get you the required dosage due to extended mixing. Okay. So let's see the effect of the vibration. And again, while placing the concrete and doing the consolidation and the vibration, that also affect air entrainment. Vibration will affect the air content, as can be seen from this figure. Vibration time, as it increases, air content goes down. However, coarse bubbles are, selectively eliminated in this case, and only extended vibration will remove sufficient number of fine bubbles to compromise the frost resistance. Okay, so that's something also to keep in mind. And again, testing, and also as equally important, control of the practices in the field, placing and consolidation. Okay. Okay, so also the effect of temperature. Temperature is also an important parameter that affects air entrainment. As you can see, the air content varies inversely with temperature. As you can see, as we increase the temperature, the air volume, the air content goes down. And this is related, as we see, okay, increasing the temperature from 10 to 38 Celsius will approximately, half the air content, will drop the air content, by 50%. The temperature effect also depends on slump, as you can see here. So, for this is 25 millimeter slump, you see the effect. And here for 125 millimeter slump, it goes from close to maybe 5.8 to 3 to 4.5 or something. Okay, so a big drop. And again, testing, trial batching, considering the job site conditions you are pouring that concrete under must be considered when deciding the dosage of air entrainment. Also, the slump has an impact. As you can see, increasing the initial slump of the concrete will result in a greater air content. That is, over the normal slump range, 25 to 150, as can be seen in this figure. This before vibration, the increase of the slump, what it does, and this is after vibration. We see how vibration reduces basically the air content automatically. Okay. So, okay, we have now looked at the factors affecting the air entrainment dosage and how they, what they do. Now let's look at the effect of the air entrainment on basically on concrete properties. Okay, so although, as we said, air entrainment admixtures are added primarily to improve the durability of concrete, they have other important influences on the behavior of both fresh and hardened concrete. For the fresh concrete, for example, air entrainment improves the workability and cohesiveness of the fresh concrete at both high and low slumps generally. Air entrained concrete is more workable than a non-air entrained mix at the same slump. Keeping the same slump, air entrained concrete is more workable and can be placed and compacted more readily than non-air entrained concrete. Okay. Also, bleeding and segregation are considerably reduced in wet mixes during handling and transportation. So about 3 to 4% entrained air, total content about 4 to 7, will increase the slump of concrete about 35 to 50 millimeters, 1 to 1.5 inches to 2 inches. So at a given paste content, the exact amount depending on the mix design and materials. This is basically due partly to the fact that surface active ingredients to some extent acts at the solid water's interface in the same way as a water reducing admixture does, as we will see in the next lecture. But the main reason for improved workability is that the tiny bubbles behaves as low friction elastic fine aggregates that reduces interaction between conventional solid aggregates particles during the placement operation. So air-entrained mixes behave as if the mix were over-sanded. That's exactly what it does. And its beneficial effects are most apparent in the lean or harsh mixes deficient in fines. Okay? So rather than using air-entraining agents to increase a slump, it is more common to reduce the amount of sand and water required to produce a desired slump. So water contents can be generally reduced between 12 to 25 kilograms per cubic meter, for a 4% increase in air content. Okay? This, partially offsets the strength reduction, because as we will see, the air-entrainment will reduce the strength, So this partially offsets the strength reduction that accompanies air-entrainment, as we will see in the discussion that follows, as I said. The improvements in workability as such that, air-entrainment may be used even when freeze-thaw protection is not required because of this, the workability. So this is particularly beneficial when mixes have low cement contents, poor aggregates grading, or harsh aggregate texture. So in this case, we use air-entrainment to help produce more uniform, well-compacted concrete. Okay? Okay, so let's see now the effect of the air-entrainment admixtures on the hardened concrete. Okay, so the introduction of additional void space with air-entrainment must have a detrimental effect on strength. That can be easily figured out. So the increased air voids are, partially offset by the decrease in capillary porosity from the lower water cement ratio that can be used. If you remember, as we mentioned, we can reduce the water cement ratio because we get more workability by adding the air bubbles. Okay, so generally, for a fixed water cement ratio, a strength loss of 10 to 20% can be anticipated for most air-entrained concretes. A good rule of thumb, though, is that each 1% of entrained air will lower the strength by 5%. However, for a fixed air content and slump, air-entrainment has much less effect and may not affect the strength of lean concrete mixes, where cement contents below 300 kilogram per cubic meter. Okay? In such cases, the higher air contents needed for good frost protection may allow expected strength, decreases to be entirely offset by the decreases in water cement ratio. So one thing makes up for another. So also there's something to know. There is an optimum amount of entrained air for good durability, as I will show on the next slide. So excessive amounts of air will drastically lower the strength of concrete and reduce also its resistance to stress from freezing and thawing. So it's a double whammy. So you're going to have to be careful about the air entrainment content or the air entrainment dosage. The high air contents generally indicate larger bubble sizes rather than smaller spacing factors. So, as well as improving freeze-thaw durability, air entrainment helps, combat the scaling caused by the ice and salts used actually on pavements and bridge decks. It also improves the sulfate resistance of concrete, because the low water cement ratio that can be used and the better compaction characteristics result in more impermeable concrete and a better overall resistance to aggressive agents. Okay, so those the interrelated characteristics or properties of concrete and how these parameters can be adjusted to account for the addition of one or more admixtures. Okay, as you can see here, as I mentioned, there is an optimum amount of entrained air for good durability. Okay, so I said excessive amounts of air will drastically lower the strength of concrete and reduce its resistance to stress from freezing. As we increase, the compressive strength decreases, and eventually its resistance to stresses will decrease. But you can see here there is an optimum air content for durability, and that should be observed. And as I said before, testing and researching the effect of basically any admixture on the concrete should be known before use, and air entrainment is no different. Okay, so speaking of the air entrainment dosage, let's look at the recommended air content. As we have mentioned, closely spaced air voids protect concrete during freezing, basically by providing reservoirs for water that exits from the paste on freezing. As I basically have shown that, let me go back, as I mentioned here on this slide, you could go back to it. Okay. So the mechanism, this mechanism, maybe it will be discussed in a later lecture, and this is really the reason. This is the reason. This mechanism, spacing these air bubbles in a certain way, is the reason for the importance for the spacing factor. Remember, we said the spacing factor, that basically a certain number from which any point of the paste should be, we should have an air bubble. But you have to remember, in practice, we have to rely on total air contents, because the air spacing, the bubble spacing is not like an easy quantity is that you can really quantify when you recommend certain dosage. So in practice, we have to rely on total air contents. Such, those used in the ACI standard practice for mixed design, which is I'm showing here in this table here, which is, I talked about earlier. Okay, which basically this, it depends on many factors, and which need not be related directly to the spacing factor. Okay, this one depends on many factors and not related directly to the spacing factor. As an example of this important point, it's illustrated in this table right here, shown right here. Look at it. It can be seen that, for a given air content, increasing the water cement ratio increases the spacing factor and increase the bubble size. Okay, as you can see. So by this lowering the resistance to freezing and thawing. So it can be seen that the air content must be increased in concretes with higher water cement ratios to maintain a given spacing factor. So the recommendations in table 8.2 here, this table, should therefore be used sensibly. I mean, they should be applied to concretes that will be exposed to severe conditions, where freeze-thaw cycles may be frequent, and where the ice and salts, for example, will commonly be used, or where we have, sulfate attacks to be anticipated. For low slump concretes, basically below 25 millimeter slump with low water cement ratios and high cement contents, air contents can be safely reduced below the recommended amounts. A suitable air void system can generally still be achieved in such concretes by using the same dose that would be required to attain a recommended air content, in this table, at a higher slump in the range of 85 to 100 millimeter. Even though the air content in the low slump concrete will fall below the recommendation, but we still get the benefits. Okay, and again, one thing to remember, if air entrainment is used only to improve workability and handling, recommended air contents can be reduced by about 1/3. So just, let's just summarize. Closely spaced air voids protects concrete during freezing by providing reservoirs for water that exits from the paste on freezing. More smaller, closely spaced bubbles, better than larger, further apart ones. Higher water cement ratio increases bubble size and spacing. So we need to increase the dosage to maintain the spacing and the bubble size. Okay? And as I said, depending on the exposure conditions, these recommendations, can be used sensibly in order to provide the required dosage, to provide the required protection. Okay, with this, really, we come to the end of lecture number 19, or lecture number 20, I'm sorry. And we finished by this, the discussion on the air entrainment admixture. Next time, we will start on the water reducing admixtures. Until then, thank you for watching and see you.